Alright, on the previous video, one of the things that we had found was that we got this equation where we had the opposite of omega squared equals x of t omega squared times x of t equals a of t. And one of the things was that this omega, we really substituted that in for the square root of k over m. So right now I'm just going to give you an equation, and we'll say that t, the period, is equal to 2 pi times the square root of m over k. I'm going to box this so that you can put it on your cards. And this just comes from the idea that omega is equal to 2 pi times f. So we could solve for f, the frequency here, and it would be 1 over 2 pi. So f would be equal to 1 over 2 pi times the square root of k over m. And then we just flip that around to get what the period is. So that's good. This is the equation that we'll primarily be using. But there's another important equation that we can get out of this, and it relates back to your labs and something that you should have seen in your labs. So what we're going to do is we're going to take a spring and we're going to displace it initially off to the side. So initially it's not moving, and this is a little bit different than what you did in your lab, but it's fundamentally the same idea. So instead of it moving initially from this point with a velocity, we're just shifting it off to the side, and now we're going to let it go. And the outcome of this is pretty obvious. There's going to be a force backwards on this, a spring force, right? And this spring force is going to try to get this back towards the origin. And one of the things that we saw in the experiment was that if you have, say, your position function, so this is position and that's time, there was something like this, where, and this is going to be a little bit different, but we start off at x max, and we're going to oscillate between x max and negative x max. So it's going to do something like this, going to come down and then go back up, and so on, in a sinusoidal type of manner. And some important landmarks here would be, if we look at, trying to find a color that's going to show up nicely against all of these. So if we started here, that might not be the color, but we'll give it a shot. Then we have, this would be the next point, where the period then is completed. So we've gotten back to the same position again, going in the same direction. So this would indicate one period. One period of motion would be this particular length, and then we'd get it again over there, and so on. Now, one of the things that we can take from this is that, yeah, we do have this sinusoidal motion, and specifically this is a cosine function. And it's obviously related to the period. So it's related to all of this, and there's actually a very nice relationship, which is that x of t equals x max times the cosine of omega t. And there's actually some more things that we can throw in there, but in this case this is all that we really need. This tells us the rate of oscillation, so how rapidly does it need to go through each cycle. This tells us where we are in a particular cycle, and this tells us how far away from the equilibrium to go in each case. We can do similar things for the velocity and for the acceleration functions. One of the things that you'll find with the velocity function is that right here it starts off at rest. So if I wanted to do a similar thing for the velocity function, then we would find that here's v max, the maximum velocity, here's the maximum velocity in the negative direction, and it starts off at 0, and it ends up initially going actually in the negative direction, right? If this is the positive and that's the negative, so it's going to go off in the negative direction first. So it actually does this, okay? And one of the things that we'll find is, and I didn't start this off actually all that well. Let me try this again. So we'll go out to here. Okay, so it actually hits its maximum velocity right when the block is passing through its origin. And then as the block goes over to the other side, this goes back to 0. As this goes back to 0, then it's being pulled back towards the center to the right. This now hits its next maximum, and back down, and so on. So this should be at point 0, and it goes through its cycles. The cycles, the rate of oscillation is exactly the same as the rate of oscillation for this function. So the frequency, you could say, for the velocity function is the same frequency as it is for the position function. Why? Because they're basically the same thing, only this one is offset a certain degree. You can see we could just take this function and shift it to the side. Now the one thing that is different is the magnitude. Obviously I didn't use x max and negative x max here. One of the things that you saw from your experiment is that if we move it further off to the side, so if I took that box and moved it even further to the side, when it passes through this equilibrium point, it's going to be going faster. And the reason for that should be pretty obvious. We have a lot more energy stored in the system through spring potential energy, and so it's going to be going faster by the time it gets back to the origin. So this is independent of the rate of oscillation, okay? The actual magnitudes, or the maximums that we can achieve, but the frequency is actually independent of how far off to the side we pull this. And that's kind of a tricky idea. The reason is, if you pull it further off to the side, it has a greater distance to cover. If we pull it all the way out here, it's oscillating between, here and here, which is a pretty big distance to try to cover. Up here, it's only oscillating between, these 2 points. So it's not traveling nearly as far. The reason why it's able to oscillate through the same frequency in both cases is because of that speed difference. This one's going to be moving a lot faster by the time that it gets to the center. So it's going to be covering this larger distance in the same amount of time. And I'm just going to construct the velocity formula here. We could do this as Vmax, the opposite of Vmax, sine of omega t. And the last one that I'll show you is the acceleration function, which is equal to the opposite of A max cosine of omega t. And what that would look like is really just like this one, only flipped around. And the reason for that, and I'll just sketch it out here real quickly. So it's going to start down here, and it's going to go up and down and so on. And it's just going to be the mirror image of this. The reason for that is because when we've displaced it as much as possible in the positive direction, the acceleration is going to be as large as possible in the negative direction. And that's the whole idea of that restoring force. And actually, if we look at this, these two equations here, this x of t equals x max cosine omega t, and this a of t equals the opposite of a max cosine omega t, one of the things that you should note is that both of them have this cosine omega t. And if we look up here, we see that, in fact, the x of t and the a of t function are almost identical to each other. We're saying that they're equal, with one exception. We have to multiply the x of t by omega t in order to make that work. And I could actually rewrite this bottom part to be the opposite of omega squared x max cosine of omega t. And now if you look at this, okay, this is exactly the same as our x of t function. So x of t is x max cosine omega t. Great. If I take that and I multiply it by omega squared, I get the acceleration function. So these functions right here really account for all of the motion that we see very nicely, and they also account for the result that we get out of the derivation that I previously did. We're not really going to use these ones too much. I'm going to focus primarily on just the simple applications, so we're going to be using the periods. And I'll expect that you're able to convert that to frequency and angular frequency as well. And that's about it for now. What we're going to do next is look at pendulums, and then we'll look at a couple of specific cases.